The piling for marine and offshore structures must be installed to develop the required capacities in bearing, uplift, and lateral resistance. So, three components are important. One is bearing and uplift, and that's tension, and lateral resistance. And these three capacities pile must be installed to develop the required capacities in bearing, uplift, and lateral resistance. For offshore bridge piers, minimization of settlements may also be the criteria. Stiffness under lateral loads, as well as strength and ability to accept the overloads in a ductile mode, are also important characteristics. And for harbor structures such as wharves, quays, and for trestle type bridges, pre-stressed concrete piles are commonly employed. Once in place, the strength and rigidity, resistance to buckling, and durability often render them the more suitable. However, stresses and strain occur during the driving, for which they must be adequately pre-stressed to resist tension, rebound cracks, and must have adequate confining spiral and hoops to resist lateral bursting stresses due to Poisson's effect. The rebound tension is at a maximum in soft driving at initiation of the installation. This is contrary to intuition. Typical piles for harbor work are larger and more heavily reinforced than those employed in land foundations. Here in this we can see typical piles for offshore construction. Here typical offshore platform piles. You see this is the water level and this is the mudline level, and from here to here 37 mm thickness, and from here to here it's a 2 1 by 4 inch 56 mm, then 69 mm, 60 mm, 37 mm. This is a thickness, different thickness, and here you can see the diameter 48 inch to 84 inch. That's a pin pile, and this is scud pile. This is a pin pile and scud pile. Here you can see pre-stressed concrete or steel piles and steel piles. Steel piles 0.6 to 1.5 meter diameter. This is a mud line. You can see it here, mud line. And typical deep water bridge and offshore terminal piles. These are the typical piles for offshore construction. Here, deep water, long unsupported column lengths, and large cyclic bending force and large lateral and axial force all combine to make a typical offshore pile, large in diameter and long in length. Why the offshore piles are large in diameter and long in length means because of its long unsupported column lengths, large cyclic bending forces, and large lateral and axial forces that makes them to be large in diameter and long in length. And piles in most offshore practice are steel piles ranging from 1 meter up to 3 meter, even 4 meter too, in diameter, and length from 40 meter to 300 meter and more. Pile capacities for marine and offshore structures can have design ultimate values as much as 10,000 ton, far above those of conventional onshore piles. Here, the dead load, live load, and zone of severe bending. You can see this is the zone of severe bending, and here also the zone of severe bending, and this is the skin friction as well as end bearing. This is how the typical pile soil structure interaction works. The typical slope is 1 is to 6, and extreme lateral force is coming from the environment and jacket. This is the jacket, and inside is the pile. And alternative methods of resisting lateral loads. Okay, and for offshore piling and bridge piers in deep water and very soft, it is customary to use either all vertical piles or to have a moderate batter up to 1 in 6 under lateral forces. The imposed deformations such as those of current, storms, winds, earthquakes, the increased bending moments, and axial forces are generally within the capacity of the piles. The batter helps to eliminate any significant residual displacement of the structure. Here we can see for resisting lateral loads, most offshore structures in deep water over 30 to 40 meter depend on the bending resistance of the pile interacting with the passive resistance of the soil in near surface stratum. Since the soil resistance is a function of its deformation, the analysis based on the interaction of the lateral load P with the displacement y at each increment level below the sea floor. So basically the soil resistance is nothing but it's a function of its a deformation. If the deformation is how much it's varying, the soil resistance also it varies according to that. And this is called PY effect. The pile must have sufficient strength to resist the resultant moments and shears at these levels to prevent biaxial buckling. The capacity to resist lateral loads can be improved by increasing the stiffness and moment capacity of the pile in critical zone near or just below the mud line by grouting an insert pile, or by increasing the wall thickness of the steel pile through this zone, or by filling the pile with concrete in this region. Fabrication of tubular piles. The tubular steel piles are usually made up of cans, rolled plate with a longitudinal seam. That means this is the tubular with the here seam will come longitudinal seam. If you see in the ISO view, it will be like this with the longitudinal seam. Individual segments cans should be 1.5 meter or longer in length. The longitudinal seams of two adjacent segments should be rotated at least 90 degrees apart. If you see here one segment, this is the seam means other next section seam should be here somewhere at least 90 degree minimum. This is one seam, the next segment seam should be at least 90 degree apart. In the cross sectional view, if you see it, this is the first segment and this is the second segment. Below it will be the segment of first one seam should be L1 here, and minimum 90 degrees should be there for L2. That's a longitudinal seam. A taut wire located at three 120 degree azimuths should be used to verify the straightness of made up of pile. APRP2A specifies a maximum allowable deviation from straightness in any 3 meter length of 3 mm. For lengths over 12 meter, the maximum deviation should be 13 mm. Then APRP2A and API RP API spec to be, this is API spec to be give allowable tolerances for outside circumference and out of roundness, as well as for bevel ends. The pile wall thickness should vary between adjoining segments not by more than 3 mm. Where a greater difference is employed, the thicker sections should be beveled on a 4:1 vertical to horizontal level. Here we can see one picture. This is a pile fabricates picture.